Nuisance stripping in ground fault protection systems can be frustrating. Let's examine the potential causes and troubleshooting steps. Firstly, consider a defective ground fault protection unit. Internal components may be malfunctioning, causing false trips. Secondly, improper wiring might be the culprit. Incorrect polarity or connections can lead to the ground fault protection receiving incorrect signals. Thirdly, ground current leakage can trigger the ground fault protection. Unintentional paths for current flow to ground can cause this. Fourthly, excessive neutral current can also cause problems. Neutral current should not exceed 50% of the phase current. High neutral current can overload the ground fault protection. Fifthly, harmonics and transients. Electrical disturbances in the system can confuse the ground fault protection sensing mechanism. Finally, mechanical vibration near the ground fault protection can sometimes cause false trips. Now let's discuss troubleshooting steps. 1. Verify the wiring. Check all connections to and from the ground fault protection, including the control fuse block. Ensure correct polarity and secure terminations. 2. Try isolating the ground fault protection. Remove the ground fault protection from the circuit and install a temporary jumper to bypass it. Check if the system operates without tripping. 3. Measure ground current. Using a clamp-on meter, measure ground current on each phase. Values should be close to 0. 4. Measure neutral current. Measure neutral current using a clamp-on meter. It should not exceed 50% of phase current. 5. Perform harmonic analysis. Use a power quality analyzer to monitor voltage and current waveforms for harmonics and transients. 6. Measure vibration. Check for any excessive vibration near the ground fault protection using a vibration meter. 7. Consult with the ground fault protection manufacturer for technical support and assistance in troubleshooting the issue. Some recommendations include: firstly, if the temporary jumper does not eliminate tripping, the ground fault protection is likely defective and needs to be replaced. Secondly, confirm that the ground fault protection is properly sized for the connected load. Thirdly, consider using a differential ground fault protection that is less sensitive to imbalances. Fourthly, install a neutral current transformer to monitor and limit neutral current. Fifthly, implement harmonic filtering devices to reduce electrical disturbances. Sixthly, ensure adequate spacing and vibration isolation for the ground fault protection. When a ground fault protection system trips when chiller number 4 is put online, consider a few specific possibilities. High inrush current when the chiller starts could be triggering the ground fault protection, even if the steady state current is within limits. Harmonics generated by the chiller's motor drives, variable frequency drives, or other components could be contributing to the ground fault protection tripping. Leakage current in the chiller's motor windings or associated wiring could be creating a path to ground. To investigate, firstly, monitor the current during chiller startup. Use a power quality analyzer to capture the inrush current and see if it exceeds the ground fault protection's trip settings. Secondly, analyze harmonics. Use a power quality analyzer to measure the harmonic content of the current and voltage waveforms. Pay attention to the 3rd, 5th, and 7th harmonics, as these are commonly associated with nonlinear loads. Thirdly, measure leakage current. Use an insulation resistance tester or megometer to measure the insulation resistance of the chiller's motor windings and associated wiring. Look for any signs of insulation breakdown or leakage to ground. Fourthly, check the neutral connection. Ensure that the neutral connection is properly sized and installed. A loose or undersized neutral connection can cause excessive neutral current, which can trigger the ground fault protection. Fifthly, review the ground fault protection settings. Verify that the ground fault protection settings are appropriate for the application. The trip current and time delay settings should be coordinated with the other protective devices in the system. If the issue persists after these investigations, consider these additional steps. Firstly, test the ground fault protection sensor. The ground fault protection sensor may be faulty or damaged, causing it to trip prematurely. Use a ground fault protection test kit to verify the sensor's accuracy and response time. Secondly, inspect the wiring and connections. Carefully inspect all wiring and connections associated with the ground fault protection system. Look for any signs of damage, corrosion, or loose connections. Thirdly, consult with a qualified electrician or engineer. Ground fault protection systems can be complex, and troubleshooting them may require specialized knowledge and equipment. A qualified electrician or engineer can help you identify the cause of the problem and recommend the appropriate solution. When troubleshooting ground fault protection nuisance tripping, remember that removing the fuse block that feeds the ground fault protection control circuit is generally not a recommended practice and may not effectively disable the ground fault protection function. The ground fault protection sensing components, such as the current transformers, may still be active even with the control circuit disabled. This can lead to continued tripping, as observed in the scenario described. Furthermore, bypassing or disabling ground fault protection can compromise the safety of the electrical system and increase the risk of electrical shock or fire. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional paths for current to flow to ground. These faults can pose a serious hazard to personnel and equipment. Instead of bypassing or disabling the ground fault protection, focus on identifying and addressing the underlying cause of the nuisance tripping. This may involve a combination of the troubleshooting steps described earlier, such as checking wiring, measuring ground current, analyzing harmonics, and consulting with the ground fault protection manufacturer. Here's more information on each troubleshooting step. Verify wiring. Carefully inspect all wiring connections associated with the ground fault protection system. This includes the connections at the ground fault protection unit, the current transformers, the neutral conductor, and the grounding electrode conductor. Look for any signs of loose connections, corrosion, or damage. Use a torque wrench to ensure that all connections are tightened to the manufacturer's specifications. Incorrect wiring or loose connections can create imbalances in the current flow, which can trigger the ground fault protection. Isolate the ground fault protection. If possible, isolate the ground fault protection system from the rest of the electrical system. This can help you determine whether the tripping is caused by a problem within the ground fault protection system itself or by a problem in the downstream circuits. To isolate the ground fault protection, disconnect the load side conductors from the ground fault protection unit. Then energize the ground fault protection system and see if it trips. If it does, the problem is likely within the ground fault protection system itself. If it doesn't, the problem is likely in the downstream circuits. Ground current measurement. Use a clamp-on ammeter to measure the ground current in each phase conductor. The ground current should be close to zero under normal operating conditions. A high ground current indicates that there is a ground fault in the system. The location of the ground fault can be determined by measuring the ground current at various points in the system. The ground fault will be located between the point where the ground current is high and the point where the ground current is zero. Neutral current measurement. Use a clamp-on ammeter to measure the neutral current. The neutral current should not exceed 50% of the phase current under normal operating conditions. A high neutral current can indicate that there is an imbalance in the system or that there is a ground fault. Harmonic analysis. Use a power quality analyzer to measure the harmonic content of the current and voltage waveforms. Harmonics are distortions in the waveforms that can be caused by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can cause the ground fault protection to trip prematurely. Vibration measurement. Use a vibration meter to measure the vibration levels near the ground fault protection unit. Excessive vibration can cause the ground fault protection to trip prematurely. If you suspect that vibration is causing the ground fault protection to trip, try isolating the ground fault protection unit from the source of the vibration. Consult the manufacturer. If you are unable to resolve the nuisance tripping problem, consult with the ground fault protection manufacturer. The manufacturer can provide technical support and assistance in troubleshooting the issue. They may also be able to offer recommendations for improving the performance of the ground fault protection system. Differential ground fault protection, also known as zero-sequence ground fault protection, works by measuring the current in all phase conductors and the neutral conductor. Under normal operating conditions, the sum of the currents in all conductors should be zero. If there is a ground fault, the sum of the currents will not be zero. The differential ground fault protection will trip when the difference between the currents exceeds a certain threshold. Differential ground fault protection is less sensitive to imbalances than conventional ground fault protection. This is because it measures the current in all conductors, including the neutral conductor. This allows it to compensate for imbalances in the system. Neutral current transformers are used to measure the current in the neutral conductor. The output of the neutral current transformer can be used to monitor the neutral current and to limit the neutral current if it exceeds a certain threshold. Neutral current transformers are often used in conjunction with differential ground fault protection. Harmonic filters are used to reduce the harmonic content of the current and voltage waveforms. Harmonic filters can be used to prevent the ground fault protection from tripping prematurely due to harmonics. Vibration isolation can be used to reduce the vibration levels near the ground fault protection unit. Vibration isolation can be achieved by mounting the ground fault protection unit on a vibration damping pad or by using a flexible conduit to connect the ground fault protection unit to the electrical system. Additionally, let's consider the specific scenario where chiller number 4's operation triggers the ground fault protection. Inrush current refers to the high initial current drawn by a motor or other electrical device when it is first energized. This inrush current can be several times higher than the normal operating current. If the inrush current is too high or lasts too long, it can cause the ground fault protection to trip. Variable frequency drives are used to control the speed of electric motors. Variable frequency drives can generate harmonics, which are distortions in the current and voltage waveforms. These harmonics can cause the ground fault protection to trip prematurely. Leakage current refers to the current that flows through the insulation of a motor or other electrical device to ground. Leakage current can be caused by damaged insulation, moisture, or contamination. If the leakage current is high enough, it can cause the ground fault protection to trip. When evaluating insulation resistance, a megometer, also known as an insulation resistance tester, is used to measure the resistance of insulation. The megometer applies a high voltage to the insulation and measures the current that flows through it. The resistance is calculated using Ohm's law. A low insulation resistance indicates that the insulation is damaged or contaminated and that there is a risk of leakage current. It is essential to ensure proper coordination between the ground fault protection settings and the settings of other protective devices in the electrical system. This coordination helps to prevent nuisance tripping and ensures that the ground fault protection will operate correctly in the event of a ground fault. When testing the ground fault protection sensor, a ground fault protection test kit is used to verify the accuracy and response time of the ground fault protection sensor. The test kit injects a simulated ground fault current into the sensor and measures the time it takes for the sensor to trip. This test can help to identify faulty or damaged sensors. In general, regular maintenance and testing of ground fault protection systems are essential to ensure their proper operation and to prevent nuisance tripping. This includes visual inspections, insulation resistance tests, and ground fault protection sensor tests. In many jurisdictions, electrical codes and standards require regular testing of ground fault protection systems. For example, the National Electrical Code (NEC) requires that ground fault protection systems be tested periodically to ensure that they are functioning properly. The frequency of testing depends on the type of system and the application. The electrician mentioned may have tried to isolate or disable the ground fault protection by removing the fuse block that feeds the ground fault protection control circuit. This action is generally not recommended and may not be effective in disabling the ground fault protection function. The ground fault protection sensing components, such as the current transformers, may still be active even with the control circuit disabled. This can lead to continued tripping, as observed in the scenario described.